Okay, good morning. All right, let's try that again. Good morning. Okay, so ready for more series? No? Well, too bad. We're going to do more series. Okay, so today we're going to finish 11.6. We've got one more test to introduce, and then we'll put this whole thing together and look at what to use when. Okay? So we'll finish the remainder of 11.6 and finish 11.7. The final test we'll look at is called the root test. And then we'll discuss strategies for testing series. Okay, so the final one, the root test, in some ways is the most restrictive one. It's useful for one specific instance, but otherwise generally not that easy to use. So let me tell you what it says. And if you look at it, it looks a lot like the ratio test in the conclusion and also in the setup. If you take the nth root of the absolute value of the terms, and you get some finite number, and as long as it is less than 1, then what that means is that the series you're testing is absolutely convergent. And remember, absolutely convergent means it also converges, right? It's a strong type of convergence. If the limit of the nth root of absolute value of an is a finite number but greater than 1, or infinity, then the series is divergent. So this is just like the ratio test. The ratio less than 1, it is convergent. The ratio greater than 1, it is divergent. And just like the ratio test, if the ratio is exactly equal to 1, then the test is inconclusive. Okay, so it looks exactly like the ratio test, except what we're testing is the nth root of the terms instead of the ratio of the next term over the nth term. So briefly, why does this work? Let's look at why if the ratio is less than 1, not the ratio, the limit less than 1 implies convergence. So if this is true, it's saying that if you take n to be large enough, this eventually approaches a finite number that is less than 1. Okay, so when n is large, the nth root of the absolute value of an is roughly equal to whatever that limit is, which is less than 1, right? That's what it says. That's what the meaning of this limit means. When n is large enough, eventually these terms start to approach 1, less than 1. If I raise both sides to the nth power, then I see that an is roughly equal to L to the n, right? If I raise that to the nth power. All this time, remember that L is less than 1. So now when I sum all of these guys together, then I'm summing up a bunch of L to the n with L less than 1. And what does this look like? A geometric series, right? It's a convergent geometric series. So therefore, we prove that if this is true, it'll look like a geometric series. Just like in the ratio test, we're saying that after a while, this thing starts to behave like a geometric series. So then we prove that this thing has to be absolutely convergent, therefore convergent. Okay, let me give you one example. And like I said earlier, this is really the most restrictive test that we have seen. It's typically only useful when the series you're testing has terms raised to the nth power, or something that looks like the nth power, like n squared here, for example. Okay, so let me apply the root test here. We're taking the limit of the nth root of the absolute value of that. But this is always positive anyway, so the absolute value is not really relevant here. So that's the thing we're looking at. And you can interpret the nth root as the power raised to 1 over n, right? Square root is 1 over 2, so nth root is 1 over n. And this way, the n squared and n, 1 over n, will reduce. And we get this thing right here. Okay, do you remember what this thing does? You have to think a little bit back to Calc 1. It's a very special number. Yeah, this goes to E. Right, that's one definition of E. You can define E in many different ways. That's one way to define it. So this thing goes to E. And the root test says we want that to be less than 1 for that series to converge. And E is, of course, greater than 1. So the series diverges. Okay? And that's not the only test you could use either. The ratio test probably could have gotten you the same result, but like I said, when you see something raised to the nth power or something that's related to the nth power, the root test is worth considering. Okay, question about the root test? All right, so let me make a summary of all the tests you have seen so far, and then we'll talk about which one is good for what kind of situation. And these are in no particular order. The first one, the divergence test, it doesn't really tell you if something converges, but it tells you if something diverges. So it doesn't give us the answer, but it's something that would help us in many situations. Right? Remember that what it says is that if the terms don't go to 0, then the series will diverge. But if the terms go to 0, series may still diverge. One example to keep in mind is the harmonic series. Right? The terms go to 0, but it does not converge. Then we have the P-series test. The P-series look like 1 over n to the power of p. That's a p. And this series converges if what happens? Right, p is strictly greater than 1. Okay? Anything less or equal to 1, this thing is going to diverge. Again, think of the harmonic series when p is equal to 1. But anything barely over 1 will converge. So in a way, the harmonic series is kind of a almost convergent thing, but just a bit short. Just a bit short. Then the geometric series test. And we know this thing converges if the common ratio has an absolute value that's strictly less than 1, right? Okay, so far these two are pretty self-explanatory as to when you will want to use them. If you see a P-series, then obviously you apply the P-series test. If you see a geometric series, then obviously you do that. So these two are pretty clear as to when to use them. And those two will form the foundation of direct comparison. You compare anything that resembles a P-series or geometric series. All right, so to do the direct comparison well, to know what to compare to, you have to know these two. And I'll talk more about how you can find out what to compare to. Then we have the limit comparison. Who remembers what the limit comparison test says? Yeah.
You choose another series that you know the convergence value of, and then you take the limit of that series divided by your test. And if it declines
Any constant?
A constant less than 1.
Greater than 0, yeah. It can be 1. 1 doesn't disqualify that. Okay, so yeah, that's good. So what we do here is we take the limit of the series you're testing divided by a known series. And if this is equal to a constant, but positive constant, then both converge or both diverge. Okay, notice I dropped the starting and end. So when you see a sigma, just think it is implying that we start at any end but ending at infinity. And in many cases, the limit comparison would be a little bit easier to use than direct comparison, but not always. So I'll give you examples again after the summary is completed. And be very careful with that one. The ratio can be 1. 1 doesn't really mean anything, but it just has to be a strictly positive constant. Okay, next we have the alternating series test. And that's pretty clear when to use that too, right? You have an alternating series, then you use that test. The alternating series will converge if the terms eventually go to 0 and what's the second condition? Getting smaller, right? The bn's are getting smaller. So bn plus 1 must be less than or equal to bn. It's okay to be equal if they all go to 0. That doesn't matter. But less than is, of course, a stronger confirmation that these things will be convergent. So that n is very important. This we always test anyway. That's part of divergence test. But this is another requirement that we have to have. Ratio test. We saw this last time. We take the ratio of the absolute value of the n plus 1th term divided by the nth term. If the ratio is less than 1, now the 1 is important here, then the series will converge. Greater than 1, the series diverges. Exactly equal to 1. Then the test is inconclusive. We have to find another test to use to determine what the series is doing. Root test we just saw. So I'll just write C, first page. Okay? No need to repeat that. We saw just that. And this is good for anything raised to the nth power. All right, what other test do we know? Integral, yeah. The integral test says the series converges if the improper integral from 1 to infinity of the function that gives us the terms converges. And we get the terms from the function. So when you put in n for x, you get the nth term of the series. Okay, now let's talk about when these things are good for. The first one, we always do it. So always check this. Right, no way around it. P-series, it's pretty clear when to use it. You use it when it's a P-series or as part of a comparison. You use this when it's a geometric series. Okay, direct comparison and limit comparison, these four can be considered as a group of things that tend to be used together, right? Direct comparison and limit comparison are based on these two. We always compare an unknown series to these things that we know very much about. So these four, consider them as one big group of tests. Alternating, again, that's pretty clear. We use it when we have alternating series. Ratio test is good for many series. Good for many. Especially when factorials are involved. That's where the ratio test really shines. But again, it's good for many. You do have to be very careful about the 1 here. Sometimes even with factorials, this will show up, so you have to have a fallback plan. Root. Anything that looks like nth power in an. Again, the most restrictive one in my opinion. And many things you can do with root test, you can also do with ratio test. So that's a good useful one to default on. Now, integral test, this requires the most work, right? Needs most work. But in principle, most flexible. In principle, if I could integrate a function, then the answer is right there. So really, it has the least restriction, but needs the most amount of work. You know, I really don't like to integrate stuff when I don't have to. But sometimes you have no other way to do it. Often useful when there's natural log of n in an. Not always, but often. Okay, so if you give me a random series that you tell me to do something with that, very often you will want to start with this. So this is a good first option. Unless you can look at a series and immediately find something to compare to. Using direct comparison. This requires the least amount of work, but requires most amount of processing. Okay, let's do examples then. Let me throw a bunch of series at you, and then we'll think about what we should do. I lost my... Oh, there's my blue pen. Here's the series 1 over n plus 2 to the n. And as usual, before we even choose a test, do the first thing you always need to do. Apply the divergence test right away. We want to see this thing go to 0. If not, then you're done. But if yes, then you are you got to choose something to do next. Okay, and this of course happens here, so yes. All right, so good news is, hey, it does pass that. Bad news is now we got to do more stuff. Yep. All right, so what do you think we should do then? We got this thing here. We have a bunch of tests. What do you want to try with? What do you want to try first? All of them. No, you don't want to do all of them. You just need one of them to tell you the answer. Limit comparison? That's a good. Okay, that's a good option. And why do you say that?
Because the highest degree, or the highest, or the largest main denominator is 2, which makes that series similar to 1 over 2.
Very good. So what he said here is that 2 to the power of n in the denominator dominates when n is large. So what he said is that this will look very much like 1 over 2 to the n eventually. Okay? Does everyone see the reasoning behind that? That's very excellent reasoning here. Make sense? Okay, so now we see this, and why is that good? Because this is 1 over 2 to the n, and that's a geometric series. So now you have two choices. You can do a limit comparison or a direct comparison. Both of these should be enough to give you the conclusion. if you apply the direct comparison here, this is already convergent. We know that already. That's a convergent geometric series. And we see that by adding more to the denominator, this will be a smaller quantity for all the n's. So this would tell us that the series is going to converge. Okay? Right, so that's one way to get the answer out of that. It's not the only way. Let's finish the limit comparison here then. What we're going to do is to take the series in question over the series that you know about. So this is the one we don't know much about. This one is the one we know very much about. And we have to deal with this limit here. And once again, we notice that when n is large enough, when n goes to infinity, that 2 to the n is going to dominate. So that n down here is irrelevant after a while. So this eventually goes to 1, right? And then what that says is that both of these series will converge, or both of them will diverge. We know this is going to converge, so the conclusion is then both will converge. Okay? Questions with these two? They're really the same thing, but any question about this? Okay. What about other options? What else could we do? If you didn't like that test, if you don't like comparison test, what else could we try? It's clearly not an alternating, so no need to look at that. How about ratio? Want to try ratio? See what it tells you? Tells us? Let's try ratio. And with ratio, you carry out the work and you pray that it doesn't go to 1, exactly equal to 1, because then all of that work is for nothing. So here's an plus 1, right? You go to an, change all the n's to n plus 1, and then divide it by an, or multiply by the reciprocal of an. All right, now we got to make a decision about this. Once again, you can use the fact that n is going to a large number to your advantage. When n is large enough, 2 to the n upstairs is going to dominate. And n plus 1 downstairs is again going to be dominated by 2 to the n plus 1. And now we've got to be really careful about this. Even though n and n plus 1 are roughly the same, but because they're in the exponent, when you raise something to something that's just a little bit bigger, it often is a whole lot bigger, right? 2 to the first versus 2 to the second. There's already a big difference there already. So if you think about 2 to the n plus 1, it's 2 to the n times 2 to the first, right? And obviously 2 to the n will cancel each other, and we end up with a 1 over 2. And that's good news. That's less than 1. Excellent. This thing converges. Okay? The one test I would not use here is integral test. I don't want to integrate 1 over x plus 2 to the x. And you don't want to do that either. Okay, so integral test is not a good choice here. All right, let's look at the next one. Okay, so we got this thing here, 2 to the n, 3 to the n, n to the n. What do you think? Yeah, this seems pretty obvious, right? Root. It doesn't mean that other tests aren't appropriate. It just means this is the most appropriate stuff. So we make that decision because we got nth power all over the place. You take the nth root of all of these guys, technically the absolute value, but they're all positive. So we can be a little bit sloppy with the absolute value there. And right away you see that this will go to 0 because of the n downstairs. 0 is less than 1, so that's great. This thing is going to converge. Okay, so that's pretty clear cut. This one's pretty clear cut. You could use ratio, but requires a little bit more work. This seems like a pretty obvious case here. Let's try this one. One over n times natural log of n squared. And this is one case where you might want to consider an integral test. Because notice that the derivative of natural log of n is 1 over n. So we can integrate this with a substitution. This can be easily integrated. That's a pretty good candidate for integral test. So what you do is you look at the terms here. Remember, we're going to think of a function that would give us these terms by putting integer values of x into here, so n, right? So this is the one that we sample to get these numbers. That's A. Okay, improper integral, we yank out the infinity, putting a symbol for that, and then take the limit, letting that a go to infinity. Let's do a substitution. Let u be natural log of x, so du is dx. Let's also change the bounds. Du is not dx. Du is 1 over x dx. What am I doing? So changing the bounds here, the old upper limit x is equal to a turns into natural log of a, right? The lower limit of 2 turns into natural log of 2. So I'm doing that just to avoid going back to x. If you don't want to do this, then you got to integrate and then go back to x and then deal with the limit. So here, downstairs natural log of x squared is u squared. And 1 over x dx turns into du. So we have this. Right? And then we integrate that, we get this. And finish evaluating that. Minus minus is a plus. And we know when a goes to infinity, natural log of a goes to infinity. So this is going to go to 0. And this is then a natural log of 1 over natural log of 2. And because the improper integral converges, then the series also converges. Okay? Besides that one, you could try ratio, but that requires L'Hopital's rule, a couple rounds. So there's a little bit of work there, but this is probably the one that will give you the result the right way. Question about this? Okay, let's do one more. N factorial over e to the n squared. Ratio, yeah, why? Factorial, yeah, that's a very, very good indication. Again, it doesn't mean that other things don't work. It just means it's the most appropriate one the easiest one to use. You don't want to integrate that, though. I don't know how you would integrate x factorial. Don't do it. Just don't. Alrighty, so we do this. Oh, by the way, what would happen if you apply ratio test to a P series? Think about it, 1 over P, 1 over n to the P. If you apply ratio test to that, we'll look at it after this thing here. So anyway, what are we doing here? N plus 1 factorial e to the n plus 1 squared times reciprocal of that, so e to the n squared factorial. And last time we showed that n plus 1 factorial is equivalent to n plus 1 times n factorial. No other test can allow you to cancel out factorial easily. This is why ratio test is very effective for factorials. So we end up getting n plus 1 from the cancellation of these two times e to the n squared e to the n plus 1 squared. Okay? And now what? Now what do we do with this? Yeah.
You could multiply out the exponent later.
Right.
In that case, you cancel out the n squared.
Right. Yeah, so at this point here, we've got to be very careful because n plus 1 is going to go to infinity. So this thing's going to blow up. We better hope this thing is going to dominate that. So this will become less than 1. So I'll do exactly what he suggested. We're going to multiply this out, right? N plus 1 square is n squared plus 2n plus 1. And so e to the n squared plus 2n plus 1 is e to the n squared times e to the 2n times e to the first. So these will go away. And now we have a very clear answer. We know exponential always dominates algebraic. This is dominating that by a whole lot. These things grow so much faster. So this is going to blow up. This will blow up at a slower rate. Therefore, this will eventually go to a 0. That's less than 1. So this is going to converge. Okay? So again, if you get lost with this series, the first one to try, besides the divergence test, you could always try ratio. Hopefully ratio gets you a good result. If not, then think about the fallback. Okay? All right, that's it. Have a good weekend. See you Monday.